Okay, now I'm live. There was one extra button I had not pushed yet, which says go live, and I had not pushed the extra go live button. There's a lot of buttons I have to push to make this thing go actually live. So hopefully I'm online now. My UI just changed again, so hopefully that means that it's actually broadcasting me live now. People can confirm that in the chat, that'd be awesome, and we'll dive into fossil stuff. Okay, that seems like a positive comment. I'm going to guess that's positive, but coming from Ralph, you never actually know these days. So let's see. So let's do a screen share, and I'll start talking about. There we go. Excellent. All right. Ralph's confirmed that I am back visible. Okay. So wasi-sockets, actually just a brief introduction before we kind of dive into it. This will be the first proposal of the ones that I've been looking at in this live stream series that I am not the champion of. So actually working with Dave Baker is the champion of wasi-sockets. And I actually met with him yesterday to talk through some of the Preview2 stuff. And so he has a PR up at this point, and so I'm going to be reviewing his PR that just looks at the update to the latest width syntax in wasi-sockets. And so we're going to focus on that and see how that looks. Depending on how that goes, we can also look at other things in this hour, but we'll just see how long it takes us to get through that stream. This means that I'm not going to be doing... well, never mind. I can still do the editing because I have my own branch of wasi-sockets. So I'll potentially still be editing things live if I want to make notes as I go. And I'll just plan to submit these things as a PR once I'm done, if I come up with ideas that I want to submit. So with that in place, let's dive into the screen share. I can push all the buttons to make this work. Okay, so in theory, I think I am sharing my screen now. And today I'm going to try a thing where I set up my screen such that I can see my thing I'm doing, but I can also see the live stream and get questions more promptly this time. Okay, so if I'm working, then everyone can see there's this Preview2 PR in the wasi-sockets repo on GitHub that I'm looking at in your browser. All right, and so the situation here is that we've had wasi-sockets been around for a while now, but it was kind of using an old version of WIT, like many other WASI proposals, and now this is a PR to update it to the latest version of the WIT bindgen tooling. Screen share is working, excellent. And so network. So previously we had resources. The resources syntax has been taken out, although we expect the resources to come back before Preview2 will actually be released. But we're taking them out for now, just so we can continue to make progress on the rest of the parts of the API. We're replacing a feature with non-blocking, set non-blocking, and subscribe functions. We'll talk about those when we get there. Replace streams with wasi-io.input and output stream. We've talked about them a bit on the earlier bits of the stream. And so feature and stream are the two big async features that will be coming in Preview 3. So that's why we're taking those out for now for Preview 2. Feature and stream will come back in Preview 3 is the big plan. And replacing stream with a custom resolve address stream. Yeah, so for name resolution, which also sort of forms a stream, we're using this. wasi-io has these sort of pseudo streams, which are based on resources and not built-in streams. And so that means we don't have type parameterization, so we have to have just byte streams. But there are other things in the API that make sense to model as streams, like resolve addresses. So we'll get to that. And adding shutdown back in the TCP module. Okay. So yeah, so we get this summary here. In fact, actually, just take a look at this summary really quickly of what this kind of looks like. So the first thing here, we got three types: TCP socket, TCP connection, TCP listener. These are U32s. These are all things that will become handles in the future when we have actual handles. But right now, they're U32s. And what that means is it's a U32 index into what is effectively a global table. Global tables are not, they don't have great properties in terms of virtualization, isolation of components from each other, and any kind of modularity. It's just like you get one table for the entire store, essentially. And so we know that this is not going to be the long-term solution. We know that these U32 indices are going to go away, and we're going to have actual resources in their place. But for now, that's what we have, and we're going to make progress. We have the interface called wasi-TCP create socket. And so that's just An interface is just a sort of set of functions that can be talked about as a group. Set of functions and potentially other things you can import or export kind of as a group. So this one has one function called create TCP socket, and it says does not require a network capability handle. So if you watch my stream in the early few days, we talked a little bit about link time authorities, and that's what this is here. So in terms of capability-based security, this is kind of interesting because it's a function that you can call. We're going to call this create TCP socket. We pass it an address family, which it's not defined here, but it's just like some enum that says like what kind of addresses we're going to talk about, which probably things like IPv4, IPv6, and potentially other addresses. So it's not actually a capability. This is just like a number we're going to pass in. And we're going to get back the return value is the result of a TCP socket, which will be a handle. We can think of it as a handle. It's just U32, but we'll think of this as a handle. And so this is a function which effectively takes no arguments and gives you a handle kind of from nothing. And so in capability-based security terms, this looks like an ambient authority. And so we want to use these sparingly. And what we're doing is we're calling these things link time capabilities. And so they're useful in this kind of situation where, especially here, where we have this create TCP socket. This will be a socket that is not yet bound to any network address. It's not yet connected to any network address. You can't use this socket in the form that it gives it to you for doing any kind of network communication at all. The only thing you can do with this socket is set socket options of various kinds. And so it's just like this theoretical resource that kind of just exists in memory. You won't actually be able to use it for any I/O. So that's actually a good use case for this kind of link time authority. It's useful to point out over here, link time authorities are still interposable. They're interposable at link time. And so that's kind of one way we can kind of retain the overall security stance that we have. All right, so we have this way to create a new socket. This basically is a direct translation, effectively, of in the BSD API of the socket function, which works the same way. You just give it an address family, and you give it a socket type. And in this case, we actually baked TCP into the type. In the BSD sockets API, the type is a dynamic thing. Here, we're going to create it statically. But that's the idea, is that you create a socket, and initially the socket doesn't do anything. It's not connected to anything. It's not bound to anything. It's just a socket that kind of exists as a data structure in the kernel memory. So then we have interface wasi-TCP, and this is kind of where all of the stuff is. So I'm going to dive into this in the actual PR because this is just a summary. It's got a lot of stuff here with no comments. I wanted to see the actual PR, so just going through the summary over first. And then we got connect and shutdown. So connect is kind of the first biggies that's going to actually touch the network. That's why we have to pass in this network, which is going to be a handle. Again, it's a U32 today, but it'll be a handle in the future, which represents the fact that here's a handle that you need to have to actually touch the network. So connect is take the socket, use it to make an outgoing connection to some other host. And then we have, that's right, I think in this API, listen and bind are sort of folded into the same thing, if I recall correctly. TCP sockets, or where is bind? Actually, I don't remember where bind is. We'll have to find out as we go. So some way to bind set local address might be, does not make a bind system call. Well, we'll figure this out as we go. Yeah, okay, so here's what's this example server. I wish there wasn't scrolling here, but so it's saying this listen call, the listen is actually doing the bind. What in the sockets API would be a separate bind step is going to be bind and listen at the same time. So we've set the local address, which is going to be presumably setting this thing in memory somewhere, telling the API what we want the address to be, and we can set other parameters, and then we can do this listen. That actually maybe will be something I'm going to take a note on before we go on here. With this new design, with these resources, with this network resource, and with this ability to create a link time authority to create a socket, I don't know that this combining of bind and listen is still necessary. I'm going to take a note to potentially look into that, because that might be something that the old API needed to do before we had this kind of organization that we no longer need to do. We could get back to sort of a standard BSD style bind as a separate step from listen. Take a look at the client. So this is the connect function. If we go back up to the thing here, so connect is the outgoing thing and listen except for incoming things. We'll talk about this more when we get there. So yeah, the socket looks like you create a socket. We do set remote address. Does not make a connect system call yet. That's interesting. Set non-blocking to true, and then we call connect and we pass it the handle. And so this will do the actual connect system call. There we go. Also with non-blocking this example. All right, so that's the top level summary. Let's take a look at the actual code. And I've created a fork. So this is just a fork of that PR branch. And this is going to be browsing the files at that branch here. UDP there's a file called wasi-udp.wit, so we'll get the UDP. We've had some discussions, I and a few other people have had some discussions about maybe UDP isn't necessary to get in here. And so UDP definitely, that feels like the lower priority of between TCP and UDP. Obviously HTTP, big use case, but a lot of other kind of protocols after HTTP that people want to use are also TCP based. There are some things that people want to do with UDP, but some of the things that people want to do, like Quick, it's not clear that we want to do Quick in WASM. Many of the use cases for Quick that I know about would involve doing Quick in the host layer and then having the WASM code talk to a higher level API. Same potentially thing with what's the WebRTC is kind of another big use case that uses UDP. Again, it's not really clear if we should if we want to do WebRTC inside of WASM or outside of WASM. These things can kind of go either way. That's kind of one of the interesting kind of design things in the WASM world. It's like you don't always necessarily think in terms of like, I'm going to link everything into my application as a single thing. In many cases, you want to actually do significant blocks of code like that in the host, especially for things like Quick, where there potentially are host optimizations that can be done that you would be able to do as well within WASM. So we got UDP is coming up. It'll be in there. But first, we're going to dive into, let's start at the top with this WASI default network.wit. So this is one of the new things. We looked at it briefly in the summary. Actually, no, this one we didn't look at yet. This is another ambient link time authority. But in this case, it's going to handle the default network. And we have to figure out I think this is going to take some iteration. So Dave and I have been talking about this a little bit. Okay, hey Dan, if Calvin Pruitt, for example, wanted to help UDP come along, is that a possibility? You can chat to help community provide that actually helps. Yeah, so UDP might be something that I and others might not work on immediately. So if people want to see UDP progress faster, that might be something where we could look at for help. We'll see how it goes. I think large parts of UDP are just going to sort of fall out because UDP, because of the way that the BSD-sockets API works, UDP isn't that different from TCP in a sockets API. There's kind of an interesting question about streams with UDP because streams really are oriented around streams and TCP gives you streams. But with UDP, the POSIX Berkeley sockets kind of approach is to say that the read system call, every time you call read system call, you get a separate packet. So the actual number of read system calls is semantically significant. It's not clear to me that we want to expose that kind of semantically significant information to the streams API, the wasi-IO API. And so that's kind of like one of the big questions that I have around UDP. I guess there are also potentially some questions around with UDP, you don't necessarily have a connection to a single address on the other side. You can have things like send to and receive from to get, you can send things to different places. There's not really a connection per se. So those would be some additional APIs we could add in there, but I think it's not that complicated. So I'm guessing that UDP is not going to be that much extra work, but we'll see as we go along. Certainly my own focus is going to be on getting TCP up and running first, and then I'm going to look at UDP and say like, well, how close do we get? So let's keep in touch. People are interested in UDP, and we'll see what we can do there. So people who are interested in UDP, I'd be interested in hearing what you want to do with UDP. I know about Quick and WebRTC is sort of two big use cases. Are there other use cases people have for UDP? And put it in the chat, put it wherever, and let me know. I'd be interested. Let's see. Okay, so I want to talk a little bit more about the link time authority for the default network. One of the things we looked at in an earlier stream this week was looking at the CLI world. what's sometimes called the command world. The name of that is sort of still up in the air. But the world where we have commandlet arguments, and we have a main function, and we have environment variables, and we have pre-opens. And if you kind of enumerate the set of handles that are going to get passed into the command program, it's potentially a large set of things. If we kind of enumerate what are all the things that a sort of typical Unix-ish, but also Windows CLI program might expect to have. And it's like, okay, we got our environment variables, we got our command line arguments, we got our file system access, and we got our, potentially beyond that, we want to add things like, we want to have like a locale. So we have like time zone information is coming in on like clocks. We need to get clocks in there somehow. We need to get, like locale might have things like the language or other kind of locale settings. We might want to have a terminal handle that would allow you to do things like the TC setEditor APIs to do terminal manipulation. There's potentially quite a few different extra handles we want to pass in. And if we look at the main function, that command entry point starts to get pretty big with lots of different stuff in it, which kind of gets awkward. It also gets awkward because it makes it very difficult to add things to it. If we want to have the concept of like you take a world and someone else wants to have that world and then want to add something to it. It's like this world, include that in my own world. So I can have like command plus a cool thing, command plus wasi-nn, or command plus wasi-crypto. These things make a lot of sense, and that's actually a really big important use case. And so having command kind of hard code, these are the set of handles that we can take, and there's nothing else, is really unfortunate. And so the idea is that we're going to add these link time authority functions for things like the default clocks. In fact, clocks already have this. There's the default clocks API is already doing this thing with these link time functions. And so default networking is following the same pattern of saying these are the things that will be passed in to it. Conceptually, would be passed into the entry point of the function. In the future, they actually might be value imports in WIT when we have that capability to do that in WIT. But for now, they're these link time functions that we can import. And we'll treat them as they're link time interposable. And we'll treat them as essentially the same kind of capability you'd get as if you passed it into the command interface. It'll be present for the entire duration of the program. And so the default network is kind of a way of saying, for most command line programs, the expectation is that you just have a default network whenever you want to call accept or call bind or listen or connect. You sort of want to just do it on the default network. And so the way this will work in practice is that your language runtime will implement the command interface, and it will squirrel away this default network probably. So that if you're doing like a C program using sockets API, libc will manage these network handles for you. All right, I'm going to skip over name lookup for now and actually go to the questions here. We have a bunch of questions going on. The shutdown function actually close the sockets. Yes, D is correct. Shutdown is the POSIX Berkeley style shutdown function, which can either it can actually close down just the read half of a socket, or close down the write half of a socket, or close down both halves. It's not equivalent to a close. Can you specify more about what the non-blocking setting changes in behavior? Yes, we'll talk more about non-blocking a little bit later, and how that works. Set non-blocking. Yes. Is D the is D Dave? Probably. So that in fact we might have the all right, the very champion at the proposal here is a likely possibility here. Okay. So let's go to wasinetwork.wit. Take a look at this interface here. So it's an interface, and we are working around a temporary restriction that actually needs to go away about importing. Actually, no, this is the interface that defines the network resource. So what we're saying here is that in the future, this will be an actual resource. We'll have a resource network, and we'll have things inside of that. So what can you do with it? You can drop it. Again, in the future, when we have real resources, dropping will be sort of a built-in part of resources, so that'll go away. But it's sort of a temporary thing. Yes, D equals Dave. Excellent. Thank you so much for showing up. And I also want to thank you so much for putting together this PR on short notice here. This is really convenient to be able to dive into sort of updated version of this today. I had planned to actually do the old version, but this will actually be really great because we can talk about the interfaces and we can talk about these link time authorities. So thanks a lot. All right, so we got an error enum. And it's my understanding that this is, so we got unknown. And again, this is just to TBD. There are a lot of error no codes in the Berkeley sockets API. And so we'll have to just do the work to copy those in here. I think similar to WASI file system, I think we're probably going to want to do the same thing of sort of rationalizing the names instead of having to deal with POSIX's historical spellings for some of these error codes. We can have our own spellings. It'll still directly correspond to things in Berkeley sockets and hopefully be clear how things correspond. Now, one thing I don't think we'll do, just to sort of call this out, is I don't think we're going to have a global error node that's going to be shared across sockets and file systems and other APIs. I think each API will have its own thing. And something like wasi-libc will have to take these error node codes and map them onto a virtual error node code for C POSIX compatibility. Okay, we got an address family. IPv4, IPv6. That's good. There are other address families in the world, but these are the two that matter most. For our purposes, at least. IPv6 address, IPv4 address. And now we're getting into like the actual representation of these addresses. I like this representation with U8s and U16s. It sort of avoids some of the endianness questions that we'd get if you represented these things as like a U32 or like a pair of U64s for IPv4. So, by the way, I'm assuming that everyone on this stream is at least familiar with TCP/IP addresses. I'm not going to dive into like how addresses work, but IPv4 is a 32-bit address. IPv6 is a 120-bit address. So we have a variant. We can have an address which is either kind. That way you can have functions that can take an address and they can work regardless of what kind of address family you're in. And we have a socket address, which then, so a socket address is we take an IP address, which is like identifying a network destination and combining it with a port number, in the case of IPv4. In the case of IPv6, we're going to combine it with a port number and this other information about flow info and scope ID. I'm actually myself not super familiar with those things. I vaguely know what they are, but I will refrain from talking about them here so I don't say something wrong. There is actually a question about whether or not those fields should belong in the socket address or whether they should probably be considered to be part of the IP address. I think we're leaving them in the socket address is where the current discussion is settled on because that's closer to how the actual Berkeley sort of POSIX API works. And that's one of the priorities here is to really enable existing code to work. And finally, we have an IP address, IP socket address variant, similar to the variant above. Variant's a really great feature of WIT. I really love how you can just say, like, I have my address can be one of these two things, and you can have a variant and say it's either IPv4 or IPv6. And if it's IPv4, you get this thing. If it's IPv6, you get this thing. It's a very concise description that can map really well onto what source languages have. Let's see, a bunch of restricted definitions. Make use of COAP, which is a restrained adapted version of HTTP, but uses UDP under the hood. Okay, we're talking about UDP use cases. Okay. That's really great. Thanks for bringing that up. Okay, and so that's WASI network. We were just talking about, we got this network resource, and we got these errors, which will be the whole error node codes eventually, and we got addresses for IP addresses and for socket addresses. All right, so then let's just talk about wasi-tcp.wit. This is where a lot of the big stuff happens. So it's an interface, wasi-tcp. So this interface can be included in a world, and it will be included in the command world. First thing we do is we have some use statements. We're going to use, we have the ability to import types from other packages. So we're going to use wasi-io defines input stream and output stream, which we'll be using. Wasi-poll defines a type called pollable, which we'll see when we talk about the subscribe function later on. And then from WASI network in our own package here, or in our own repo here, then we're going to find that the network type we just looked at, the error type we just looked at, and these address types that we're looking at. We'll pull those in as types we can use here. Yeah, good point. UDP use case, manual DNS querying. That's a really good point. Okay, TCP socket handle is U32. And the thing you have to know when reading these APIs right now is if you see a random type that's just a U32, it's probably talking about a resource. It's on my to-do list to sort of establish a convention for how we can comment these things. So later on, when we have resources, it'll be really easy to go in and find all the resources. But I think we don't have that many of them. It'll be pretty easy to find in any case. All right, so enum shutdown type. This is actually the shutdown function. This is what it uses to know what to shut down. So you can shut down the read side of a socket or the right side or both sides. Shutdown actually can be semantically significant. So if the other side is a server and it's waiting for you to send requests and then get responses, when you do a shutdown on the send side, that actually can notify the server, I'm done sending. I won't be sending anything else. And so it can know that. It can send you back the full response and appropriately respond to the fact that you're done. Whereas otherwise, if you just send the message, it'll keep the send side open and the server won't know if there could be more coming. So the shutdown is the way to tell the server, I'm done. All right. I guess we can talk about that at the shutdown function, but let's dive into create TCP socket. So this is a new socket. What do we got here? We got a network, an address family, and a result. So this actually is this is different than what we had in the original PR description. We had this wasi-TCP create socket. So I'm just going to guess that because I put Dave on the spot here and didn't give enough time, that it's just not all synced up yet. Yes, exactly. So that's totally cool. I know that this is all happening very fast, so we will go with it. And I think what that means is that we have to sort of imagine in the future, this is going to look like there's this create TCP socket in its own interface for creating these things. It will not take a network. It'll be a link time authority. It'll still take an address family, and it'll still return TCP sockets in an error. And so as with Berkeley sockets, you create a TCP socket, and the very first thing is it doesn't do anything. It's not connected to anything. It's not bound to anything. It's just a socket. And we have a function to drop it, because you need, this is basically close in POSIX. And then we have a bind function. And so I think I actually mentioned this in the earlier thing when we looked at the earlier API. Exactly, if bind and listen end up being separate functions of the same function, that can be something we can iterate on. It can work both ways. I don't have a strong opinion about which way is the right way. It's a little nicer if we can split them into separate functions just from the point of view of POSIX compatibility, because POSIX gives you this bind as a separate step from listen. But honestly, we can make anything that people want to do work either way. So kind of up to like whatever is most practical. It's kind of how I'm looking at this. So bind in Berkeley sockets, the function of bind is you have this socket which is not, there's no network address associated with it. It's just like this abstract thing that you can set socket options on and nothing else. Bind says take that socket and bind it to an address. So we're going to pass in socket to bind. We're going to pass an address to bind to, a local address. So this is saying like I want to take this socket and attach it to this thing, this address that I have. If we do this with the network handle. If we move network handle out of the creation of TCP sockets, then it'll go into the bind function. So that bind would need to have this handle in order to bind to the address. But even with a bound socket, the socket's not listening to anything yet. So bind is just like, let's connect the thing to the socket. I'm going to take a result. And yeah, so bind, the return value of bind is, in the success case, you don't get anything. You just like see the bind. And if it succeeds, then you're like, okay, do the next thing. If it fails, you get the error no code. So we're not returning anything. And then, okay, so we'll go a little bit out. We'll just follow the order of the PR here. This is like not in the logical order that you would do things in if you're a user of the API. So we'll just like follow that order thing. So that's maybe a bit of feedback. It might be kind of nice as a note that I'll take in the future to organize this file in kind of like a logical order. So like, like socket and then bind. And then listen might come next after bind, or and then accept after that. So we can talk about those when we get there. Local address, take a TCP socket, and it'll tell you what local address it's listening on. This is like, it seems like it's a little bit redundant because you just told it when you did a bind, you said, here's the address I want you to listen on. It's just like telling you that back again. But there are situations where you might receive a socket from somewhere and not know what the local address is. So it's good to have a way to query that. And connect. Okay, so yeah, so connect is for outgoing sockets. This is the way I want to do a fetch. I want to do an outgoing connection to something. Make a database connection. I'm going to initiate the connection on my end and tell the other end, like, I would like that to connect with you. And then it can either accept that or deny it. So we transition to connection states. This corresponds to certain packets in the TCP protocol, if you're familiar with that. But basically, this is saying, like, I want to take this socket, and I want to connect to this remote address. I'm not going to pass it. And here, my result is going to be a couple things. We're going to tuple, which is just 2 values, and it's going to give you an input stream and an output stream. So streams in this iteration of, in fact, streams in the future iterations as well are unidirectional. So streams in the Preview3 streams, as well as in these Preview2 resource-based streams, are all unidirectional. So there'll only be an input and only be an output. So like it's a little bit different than the POSIX socket concept, where a socket is just this thing you can do read and write on. Here we're going to have separate stream objects. And so when we expose this as a POSIX compatible API, for people that are expecting to have a single file descriptor that can do everything on, libc will actually take responsibility for mapping those things. So you'll have a single file descriptor from C code or from high-level code that would talk to those APIs. And then it'll get mapped when you do a read, it'll get mapped to the input stream handle. When you do a write, it'll get mapped to the output stream handle. So we're going to get this pair of streams back from this thing. And I should make a note here. One thing that might be missing here, I think, is that I think Connect wants to return an additional socket handle as well, because you might want to take those streams and set socket options on them independently. By the way, I apologize if there's some noise in the background. There's nothing I can do about that noise at this moment. Okay, so Connect, I'm going to make a note of this, might want to return sockets. You can use the set socket options on that connected stream, because what with Connect is you get, let me make sure I know what I'm talking about. Actually, no, I'm incorrect here. I was thinking that Connect was, I'm getting Connect and accept mixed up. So I don't do sockets APIs every day. I have done sockets programming in the past and I'm familiar with it, but I forget exactly which things we do. So Connect doesn't give you a new socket. So Connect is just going to give you these new streams. But that's potentially interesting because I guess that just maps up how Berkeley works. So so we'll go with it for now. I'm going to make a note to think about that more, but that's an interesting property. We got a question here. What's the considerations around the getter-setter interface versus having a record with fields for the wasi-TCP? Oh, so for things like local address, is that what you're talking about? I'm not sure exactly what you're talking about. I can say in general, it's a desire of APIs in general to avoid having fields that can be mutated, especially for setters, because that's actually potentially a way to step around the capability-based security model. It's like one of the sort of classic loopholes is that you can have the ability to directly store to a field. There's no way to interpose on a store, and so in capability terminology, a store to a field is not refusable, whereas everything else in the API can be refusable. But if I get a handle, I can call methods on it, and those methods could be refused, but I could do a store to that handle, and it would not be refusable. And so in general, we're going to avoid exposing sort of mutable things you can set to directly. We're just going to have APIs like setters you can set. And that's actually, there's several reasons why it's good to have that. I talk about it in terms of capability-based security, but you can directly translate that into kind of practical purposes for, like, if I want to have an intermediary that can control what settings you can set, or I want to have someone who can log all the things that you're doing with this API, I want to log all the settings. Stores to fields wouldn't be visible to those kind of intermediaries. So you wouldn't be able to log settings in the fields, at least when the settings happen. So making sure everything is an API is the way to do it. And then if you're worried about efficiency, thinking like, well, a single store to a field could be faster than a call to a function. The plan for addressing that would be to have engines inline the functions. And potentially there could be hints in the future to tell engines that this is a setter. You might want to consider inlining this. Or maybe for some of these setters, implementations will just do it on their own, because if the code is simple enough, you can inline this down to a single store instruction in some cases. And so that's kind of the path forward for optimizing these things, to think about inlining. All right. So I need to think more about this connect thing, and figure out how that works. So gracefully shut down the connection. So now we're talking about the shutdown function. We talked about this a little bit before. So we can shut down the receive function. That's saying, I'm not going to listen to any other messages you send me. I'm shutting down my receive side, and if I try to read from this thing, it won't even work anymore. Send says I can shut down my sending side, so I'm not going to send any more messages. I can't do any more writes to my output stream. Or I can shut down both at the same time. It does not close the socket. That's right. The socket stays open. Resource remains allocated. And if you don't have to do a shutdown before you close the socket, you just close the open socket and it'll automatically shut it down. Fails when the socket is not in a connection state. So I'm going to make a note to make a note. We should comment that closed as a shutdown effectively. Okay, so we got TCP, we got a shutdown type. That was the enum we saw earlier, and it doesn't return anything. Good. Okay, so listen. This is for the incoming connection side. This is for the server side, conceptually. And so we have a socket that's a TCP socket. And in the listen case, this is where you definitely do get, or sorry, listen, I get listen except mixed up. Okay, listen, we're not getting, so listen is like, okay, now we're just gonna, the comment fact is the exact thing I want to do here. So start listening for new connections. It transitions the socket into the listener state. So listen says, like, you already, so in the sequence above, like, we already did the bind. We created the socket, we did the bind, we give an address. Now listen says, like, actually go out to the network and start listening. Like, so someone else starts sending us packets. Now we're actually going to have the network stack in the OS is going to start talking to those packets. We're saying we're listening now. Listen doesn't actually make the connection, but says we're going to start listening for one. And so we return nothing. There's something to return back here. We listen on a TCP socket, and we get a backlog size hint of U64. And so that's just talking about the backlog is like how many potentially like connection. If everyone's trying to connect to me at once, how many people can be connecting before we're going to start dropping them? The remote address. So once someone does connect, you can get the remote address to tell you what's the IP address of the other side, the socket address, in fact, the full socket address with the port of the other side of that. And that's a get peer name in POSIX. So except, now here's the function where we're going to take the socket and we're actually going to get a new thing out of it. We're going to get a new socket handle. This is the thing I've been waiting for. I keep expecting to see it. But of course, it's except. This is the thing that does it. So except is the thing that takes a TCP socket and gives you, if it succeeds, three things. It's going to give you a new socket, which kind of represents the connection that you made, as an input stream to read from and an output stream to write to. So we get three handles, and your language standard library will manage these handles for you. So if you're using the Berkeley API, you still have a single file descriptor that will then map to these three things. So you do get sock opt, goes to the TCP socket. You do read, goes to the input stream. You do write, it goes to the output stream. So it'll all look like one interface to you if you want to have that interface. But of course, it's also an option to not use the POSIX API. So you want to talk to this API directly, you can do that as well. And for some use cases, you might want to do that, and you don't even need to hold on to the TCP socket in those use cases. You just take the input stream and output stream and just read and write if you don't need any more socket options. All right, so we've got a couple of socket options here. Keep alive is the so keep alive option. So this kind of gets into like sockets lore. You kind of just like know some of the popular options that people set to optimize and configure how servers work. So I actually have to admit, I don't know what keep alive does, or I have a vague idea, but I don't know enough to describe it confidently in this context. So this is just the so keep alive option. If you know what that is, this is it. It's a standard feature of sockets. Same thing with no delay. There's a Boolean flag, there's a getter, there's a setter. It sets the option. They return result of bool, and this just takes a bool and returns nothing. And of course, all these things can fail with the error no code. Kernel buffer space reserved for sends and received on the socket. Yeah, so more parameters. this for if you want to tune, your kernel settings for the buffer that will be used to implement your TCP socket. You can set the buffer size and you can get it. On the receive side, you can also set a separate send buffer size. It'll be interesting to see how these kind of play out in a WASI context, to see if these buffer sizes kind of like the optimal buffer sizes we want to optimize for will correspond to the same thing you want to use on a native server. I actually don't know if that's going to turn out to be true, but we'll see where that goes. The address family, just a simple query function, take the socket, tell me what address family it's on. Interesting that this is infallible, so there's no result on here. It could just always succeed because the protocol stack should always know what address family it's on. And then we got Unicode hop limits. So these are more get sock opt, set sock opt things to get and set socket options. And there will almost certainly be more socket options in the actual Berkeley API on various platforms. Like Linux has a whole bunch of Linux-specific things. Other platforms have their specific things. And it'll be kind of interesting discussion over time when you talk about wanting to add more of the options, and it'll be sort of a portability versus configurability, performance, throughput kinds of conversations. But the set here, I have not researched how portable these things are. And so we'll just go with it. Equivalent to IPTTL, IPv6 Unicode hops socket functions. So it's setting limits on how many hops you want to have. Okay. And then IPv6 only, dual stack mode, there it is. Yeah, there's an interesting discussion about whether or not dual stack mode should be on by default or not, because some people want it, some OSs have it, some OSs don't. Different options there. I think we can leave this as is. I don't think I have anything unique to say. There's been a pretty significant discussion on this on the wasi-sockets repo if you are interested in digging into that. I don't have the link handy though. Get set the blocking mode of the sockets. Yeah, so non-blocking. Okay, we want to talk about non-blocking. Here we go. Okay, so this is actually pretty close to, we've got a few different iterations of how non-blocking can work in this. And so what's here, set blocking and set non-blocking is pretty close to what you get in POSIX or Berkeley sockets. In that you sort of have this FCNTL, which can set the, or sometimes it's an ioctl on some platforms, sometimes it's FCNTL, to set the flag which says blocking or non-blocking. And the way it works is that when that flag is set, then operations on it that would block, if you're doing a read and the kernel doesn't literally have data sitting in its buffer ready to go, it would block and wait for the network to provide data. In that situation, if the socket is in non-blocking mode, then the socket will simply not block, and it'll return with a failure in the result. All the reads and writes will return results, and they'll fail with the error code of would block. That actually reminds me that because we'll actually be doing the reads and writes through the wasi-io proposal, wasi-io is going to need to have a way of returning would block. So I'm going to make a note of that right now. So we need to have would block on its streams. This will almost certainly change in terms of how we deal with non-blocking sockets in Preview2 when we have actual async. But for now, I think it makes sense to sort of stick pretty close to the Berkeley sockets approach of saying there's a flag, you can be in non-blocking mode or blocking mode. The default assumption, if you're passing a socket into code that doesn't know what you're doing, is that the socket should be in blocking mode. Because if someone takes a socket, they expect to be able to take a stream and do a read from it, and be able to get a read result and be able to get bytes from it. If the socket is in non-blocking mode, you can't just take a socket and just read from it. You have to do a poll first to sort of wait for the data to become available, and then you can do a read, typically. You don't have to do that, but that's typically how you do it. You do a poll and wait for a bunch of sockets, and then when one becomes ready, then you can do a read. And if poll told you it was ready, then the read would probably have data that you can read from, and it'll work. But if you just try to do a read on a socket that's non-blocking, and you just do a read on it and expect it to work, you'll probably fail with would block. And so it's typically not common to pass around sockets to code that's not expecting them to be in non-blocking mode. Yeah, so exactly. They're planned to be removed when async is natively supported. And it will have, most likely what we'll do when we have native built-in async, we'll just make all sockets, put all of them in non-blocking mode. And then we'll say the responsibility of emulating blocking APIs for POSIX compatibility for other languages that want to have blocking APIs, we can do that in WASM. We can have WASM's going to have code essentially like WASI-libc, for example, could have code that does this if the user calls read on a non-blocking socket that they didn't think was non-blocking, then we'll just do a poll, and the poll will block, or what Preview2 will call wait or block, is it'll just wait. And that might suspend the stack. Other things might happen. Other async work might happen. But from the point of view of the code calling the POSIX API, it'll just look like you're just blocking. And then when that's ready, then we'll do the read, and we'll give the data back. So we can implement POSIX semantics on top of Preview2 async for compatibility. But what we might do is basically say, other than that compatibility there, we're just going to mark all sockets non-blocking. Whenever you give me a socket, I'm going to mark it as non-blocking in my WASM engine, and just really lean into the async mode, because I think that's kind of the future of where we want to go with networking, is just think async first for all the things. So probably in the future, we'll move to everything is non-blocking, and we emulate blocking on top of that. Right now, I think it makes sense to sort of stick with the simple thing, which is pretty close to Berkeley sockets and doesn't get us too far away from where we started. And is pretty well understood. I think most people are working in this space are familiar with putting a socket in non-blocking mode and using something like poll to wait for it. All right, that's my story for sockets right now. If people have questions about it, I'm certainly happy to answer questions. You can hear me better than the noise, so it's okay. Excellent. Ralph stepping out. Considerations around the getter setter interface. I think I answered that one already. Okay. Yes. So, and that's the bottom of the file. We need to subscribe. Oh, but we got to talk about subscribe. So I talked about poll and how poll works. Pollable is defined. That's one of those types we implemented at the very top. We imported type pollable from the WASI poll proposal. So actually, if you check out the WASI poll repo in the WASI poll.wit.md file that's in that wit directory, you'll see the poll type defined there. And so pollable it's a U32, which is representing a handle, which will be a handle when we have handle support. And the way the poll one-off function works in Preview2 is it just takes a list of pollables. This is kind of a nice improvement over the Preview1 poll one-off, because in Preview1, the poll one-off function took a pointer to essentially a union, and it kind of required this kind of closed set of everything that wants to be pollable has to kind of be in this union. The poll API kind of has to know about everything. Now with this pollable API, we can kind of factor that out. So we can have a proposal like this, like wasi-sockets, that can return a pollable object, and we don't have to have the poll API itself kind of know about this. In the host implementation, it still will have to know. This Preview2 iteration of APIs still will require that the host implementation of things like sockets and poll have to know about each other, because poll is going to take the host file descriptor, and poll it. So we still have to have some coordination between the implementations, but we can talk about these WIT files as saying wasi-TTP just returns a pollable, and then poll one off can poll for any pollable thing. So subscribe, just you get a socket, it gives you back this pollable, which is a handle, which is just this thing that represents I want to be able to wait for this thing. You can get a pollable from a socket. You can also get a pollable from a stream. You can also get a pollable input pollable from a stream or output pollable from a stream. You can also get a pollable for a clock. And you can use that to implement a timeout function. So you go to the monotonic clock and you say, subscribe to the monotonic clock. This is in WASI clocks. It'll give you a pollable thing, and then the poll will wake up when that amount of time has expired. So you can say, I want to get a subscribe to a clock for 5 seconds in the future, and then that poll will wake up the poll at that time. That's kind of how we implement timeouts. It would be a timeout parameter in the POSIX poll API. All right, now we made it to the very bottom of wasi-TTP. We made it to the bottom of this file. We still have 7 minutes left. Let's take a quick dive into wasi-UDP. I hope this is quick, because I want to talk about name lookup too. wasi-UDP.wit. This is similar. So UDP has multiple differences from TCP. One of them is that it's not sort of reliable delivery. We don't have a stream concept. We have datagrams. And datagrams aren't just bytes. They're sort of structs, and you can kind of get a whole datagram, or you might miss datagrams. They might come in out of order. And so we get a datagram. It's a list of U8. Theoretical max size. In practice, this is a little bit tricky because the practical size of a datagram is limited by the MTU of the network. And we ideally like to avoid exposing WASM to kind of the knowledge of the MTU of the network, or having to define what's the biggest MTU you can possibly use in a portable way. So that's kind of something we have to do a bit of thinking about is MTU versus the size limit here. And also datagrams, because there's no connection, you can have a UDP socket that can receive datagrams from multiple addresses. And so the datagram gives you not only the payload, but also the address of where it came from, which host sent it to you. And there's lots of other stuff we could add here. We can add the local address. The local address you received it on. You can add the local interface you received it on, and the other parameters you can get about the datagram coming in. So UDP socket, here's another resource. Create UDP socket, drop UDP socket. I'm going to go pretty quickly over these things because it's very similar to TCP. Bind. Bind is a little tricky for UDP, but there is a bind for UDP. So because UDP can either be like bound to a particular address, or you can sort of have an open-ended thing. Although I guess maybe we're saying here we're going to disallow wildcard binds as long as there isn't a way to pass local address to a send and receive. Yeah. So there's some work here. I'm not going to dive fully into this. There's some work here to figure out how do these open-ended wildcard binds work. Local address, take a socket, return the local address, very similar to TCP. If we're bound, we might not be. Receive. So we got send and receive. So before we had read and write, we're going to go through our streams. Now we have send and receive on the socket itself. This actually might be the answer to the thing I mentioned earlier about how there's a semantically significant calls are semantically significant. So every time you call read, it'll give you one packet. And if your read buffer is too small, the default API will just truncate the packet rather than giving you the whole packet. It won't wait till you call read a second time and give you the rest of it. It'll just like say that read call corresponds to that packet. That's a little awkward to do within the stream API. So we might say, if you want to read and write on a UDP socket with these datagrams, you'll have to use these special send and receive functions, which can return you a datagram, which can then have its own promise of, you're going to get the whole packet here. Not have to worry about truncating packets. So that makes sense to me. And connect, remote address, and we got the whole suite of socket options again. It's possible we want to look at factoring out some of these socket options, but there's not that many of them for now. I'm going to make a quick note about that. Factor out socket options. It's quite possible that Dave's already thinking about these things. Again, I'm sort of reviewing this on relatively short notice, so I thank everyone for your patience here. Yeah, non-blocking and blocking is the same thing for TCP, and that's the end. So basically UDP is very straightforward. A lot of the stuff will just fall out. When we implement TCP in engines, a lot of the implementation will just work for UDP. We have to think a little bit about these datagrams, send and receive, and these wildcard UDP things. It's nothing to think about. But other than that, I think it's pretty straightforward. There might also be some other corner cases to think about, but I think overall it's going to be pretty straightforward, is my guess. Yeah, so let's take a quick look at WASI name lookup in the last few minutes we got here. And so all the addresses we're looking at are the numeric IP addresses. And of course, people want to deal with host names rather than IP addresses. They want to do DNS to look up addresses from names. And yeah, this is a thing that I think there's yeah, exactly. There's some of what we're seeing here is also kind of working around the limitations of WIT, and so that's been a thing that's been evolving over time, and so we'll just continue to evaluate what we can do as WIT features become online. So looking at DNS, there's really not that much here in terms of the API surface area. There's just we got non-blocking mode, we got some subscription stuff we can do, but really the big picture is we can say resolve address. So we're going to give it a network to resolve in. We're going to give it a name, which is like the host name if you want to resolve, like example.com, and an address family that we want the address for, which might be optional, which if we say we don't give it one, then we're going to, I think, say that you'll take any address. And include unavailable, which means I want to get all the results, even things that are unavailable. And the key part for this is we're going to get back a resolve address stream. And so this is something I just talked with Dave about yesterday. This is why I know about this. So the idea here is that we're actually going to want eventually a real stream. This will be a Preview2 stream type. With the parameter type of that is going to be these resolve address records. For now, we're going to sort of emulate that with like a custom resource that will have essentially like an iterator like API. Because when you say DNF resolve some name, there might be potentially multiple addresses that are going to come back that are the resolution of that name. So we're going to get a sequence of these things, and they may not all come back at the same time. And so eventually we might want to wait for them each individually. So it's going to be like this iterator of like, give me the next one, give me the next one, give me the next one. So we have resolved address stream. That's our resource, this stream that we just created for resolving addresses. And we can say, give me the next one. So give it that stream. Oops, I didn't want to do that. And we're going to take these results and go option IP address. And so the option is sort of the stream convention we have here for like when it's some, that means I have an address to give you. When it's none, that means you've reached the end of the stream and we're done. And there'll be no more addresses from that stream. And we can drop it. Again, these drop functions will go away when we have real resources, but they're useful for now because we need to be able to free up resources. You can set DNS resolution to blocking or non-blocking. Sort of historically, a lot of things in the C API, POSIX API, were blocking, but DNS resolution is one thing that a lot of people really want to do in non-blocking mode. It's very common to want to do a lot of different DNS things and have other async work happening while you're waiting for the DNS query to complete. So people want to set their DNS resolution to non-blocking, in which case this stream will act in the same way that we talked about for the TCP socket streams when they're non-blocking mode. So if you try to read from it, or you try to call this next function on it, it's going to give you a result, and if the DNS record isn't available yet, the result will just come back and say, I'm not here. You're going to get a ewoodblock error from the result. And if you want to wait for a result, if you're in non-blocking mode, you want to wait for a result and potentially wait for other things at the same time, then you can call the subscribe function. And you can do the same thing. Again, you get a pollable. So this is factored out pollable thing. Any API in these WASI APIs that's willing to be cooperating with WASI poll on the host can return a pollable thing, which means you can plug this into your poll function and wait for this at the same time that you're waiting for other things around other sockets or other streams or waiting for a timeout. They can all be waited for in the same function call. And so that is it. I think it's actually pretty important that this resolve addresses takes a network handle. So DNS resolution is a kind of network communication, right? You're going to send out queries over the DNS protocol. Okay, so we're live here again. I forgot that the streaming software I'm using here cuts out at about an hour. And so at the end of the stream, I'll give you a real end here. I'll actually end it up here. Thanks a lot, everyone, for tuning in. We just walked through wasi-sockets. This API looks like it's in pretty good shape. I know I obliged Dave to scramble a bit to put together this PR, and I greatly appreciate that. But I'm really optimistic where this is going. This API looks like it's in good shape after we sort of finish up this kind of little iteration and updating to the WIT stuff. As we progress forward towards the Preview2 hitting production use cases, we expect to have real resources coming online so that all these U32s will go away and be replaced by resources. And that'll clean up the API in a bunch of ways. And so things are in pretty good shape. And that's all I have now. If you're interested in future streams, follow me on social media. I am Sunfish on the Hackaderm social media website. Post that link in here. And I can't pull it up right now, but all right. I don't know why I can't pull things up in my browser right now, but thanks a lot for showing up, and hopefully we'll do more streams in the future. If you want to see me do more streams in the future, reach out and give me topics to stream about. That actually would be really helpful to see what things we should do. I think we sort of made it through all the WASI APIs, and I'll kind of be looking for good ideas of things to stream in the future. Some of the times the work in WASI is somewhat open-ended, trying to figure out what's going on, and I think those are harder to stream because I don't necessarily know where they're going to go. These API reviews have actually worked out pretty well because I can just walk through the API and talk about them as I go. So if people have ideas for other things that would work well in a stream format like this, let me know. Thanks a lot, everyone, for showing up, and hopefully see you around in future streams.